So let's now look into our first scheduling algorithm, which is the simplest and most intuitive algorithm, but we don't expect it to be the most efficient one. Okay, so it's just first come, first serve. First come, first served. If you have a bunch of processes like P1, P2, P3, and P1 arrived first, then P2, then P3, so schedule them in the order they have arrived. So do P1, then P2, then P3. By the way, we assume that P1 arrived at time 0, P2 arrived at time 0 plus delta 1, and P3 arrived at time 0 plus delta 2, where delta 2 is greater than delta 1, and both delta 1 and delta 2 are much smaller than the CPU bursts. So there are small deltas that will distinguish between these processes in terms of arrival time, but these deltas are negligible when it comes to calculating delays, and they are negligible compared to the CPU bursts. Okay. Okay, so in this case, what's the average waiting time? P1 is going to wait for 0 time. P2 is going to wait for 24 time units. And P3 is going to wait for 27 time units. And we take the average of 0, 24, 27, and the average is 70. So this is our average waiting time. So now the question is this a good algorithm? And if you were doing the scheduling, would you do it in this order here or not? So is this good? Is this scheduling algorithm good? If our objective is minimizing the average waiting time, is this good? No. So how would you order them or schedule them in order to minimize the average waiting time?
Shorter ones go first.
Yeah, exactly. So if this is very intuitive, right? If our objective is minimizing the average waiting time, so we must do the shorter jobs first. And in fact, this is going to be the next algorithm. So the next algorithm is shortest job first. Shortest job first is an algorithm that schedules the shortest job first. So we have, this is another example. We have these processes with these CPU burst times. So we're going to schedule them in order of CPU burst. So which one is the shortest? P4. So we put P4 first. Then the shortest is 6. So we put P1, 6 for P1. We put P1, then P3, then P2. Now the average waiting time is, how long did P1 wait? P1 waited for 3 time units. How long did P2 wait? P2 waited for 16 time units. How long did P3 wait? P3 waited for 9 time units. How long did P4 wait? Waited for 0. So the average is 7. And this is the average waiting time. And in fact, it's optimal, if our objective is minimizing the average waiting time, shortest job first is an optimal algorithm. This is very intuitive, so intuitive that we will not provide a proof, a formal proof of optimality of shortest job first, because it's just so intuitive. Now, what will the waiting time be if we do them in first come, first served? If we do first come, first served, in this case, then P1 will wait for 0 time. So this is the process. This is the waiting time. Process 1 will wait for 0 time. Process 2 will wait for the duration of process 1, or the CPU burst of process 1, which is 6. and process 3 will wait for the burst of P1 and the burst of P2, which is 6 plus 8. And P4 will wait for all of them, so it's going to wait for 6 plus 8 plus 7. Okay, and you sum all of these waiting times, you divide it by 4, and you will get 10.25. So there's a significant difference in average waiting time between shortest job first and first come first. So, okay. Now, first of all, when we study these examples, we assume that each process has a single CPU burst, only to simplify things. Okay, just so this is a note that in our study of scheduling algorithms, we will assume that each process has a single CPU burst, only to simplify things. Now, this shortest job first looks perfect. I mean, it minimizes the average waiting time, and it's optimal, and it seems to be the perfect algorithm. But what's wrong with it?
It'll continue to push jobs that have a higher burst time to the end.
Okay, and yes, so in fact, this is a problem with all kinds of priority-based algorithms. So shortest job first is a priority-based algorithm where the priority is the length of the CPU burst. Shorter bursts will give higher priority. Shorter bursts will give higher priority. It's a priority-based algorithm, and generally speaking, in any priority-based algorithm, we have a starvation problem. So what you have just described is a starvation problem. You know, remember when there are priorities, you have the risk of starvation, because lower priority processes, which are processes with longer CPU bursts, will have lower priorities and may be waiting for a long time in the queue. Now, well, starvation is a problem that any priority-based algorithm faces, and operating systems have solutions to this starvation problem. What do you think would be a solution for the starvation in this case? Yes?
You put like a max waiting time on a process.
Yes, so that could be, the solution is along this line. You can set a maximum. It's just a maximum from a practical point of view is hard to implement because you can never control the time. There are so many things happening in the system. But yeah,
You could do, you could say that each process won't wait more than, won't let more than a certain number of processes finish before it.
yeah.
So that way you're not having to measure the time.
So this is bounded waiting. So and from implementation point of view, a good way of implementing this, or a practical way of implementing this, is to boost the priority of a process when it has been waiting for a long time. Generally speaking, for any priority-based algorithm, if a process has been waiting for a long time, you boost its priority, and this is what we call aging. Okay, so this is a solution. But there is a problem with this shortest job first algorithm. There is an obvious problem in actually implementing this from a practical point of view. So now imagine you're trying to implement this in a real operating system. You are writing operating system code and you are implementing a real operating system. What will be the main difficulty that will face you? Yeah.
How do you know the burst time?
Yeah, exactly. Yeah, exactly. That's the challenge. How do you know the CPU burst time? So we have them nicely here on in this slide, and we're assuming that we know the CPU burst times, but a real operating system will have to schedule the next CPU burst, right? You are a scheduler and you're trying to schedule the next CPU burst, not the previous CPU burst. The previous is done already. Your job as a scheduler is to select a process to get the CPU next. So it's all about the next, the length of the next CPU burst. And how do you think a real operating system handles this problem? You know, if you were writing a real system and you would like to use a shortest job first type of algorithm, and the challenge is to know or to estimate somehow what the length of the next CPU burst is. And as an operating system, you don't know the future. Right? So the operating system is has all kinds of privileges. It can execute privileged instructions and it's in control of the system, but it's not magic. It doesn't know the future. So what do you think makes sense for the operating system to do in this case?
Is there a way for the operating system to determine how much I/O a certain process might require?
Nothing about the future. It doesn't know about the future. You know, the system is just executing this process operation by operation. Operation 1, operation 2, operation 3. And the operating system doesn't look ahead. And the operating system is not in the business of analyzing a process and trying to determine what the process is going to do. Operating systems do not analyze processes. Unlike compilers, for example. When a compiler translates a program from a high-level language into machine code, it analyzes that program and it does certain kinds of optimizations based on its analysis of the program. But an operating system does not analyze a program, does not analyze a process, and it does not comprehend the process. It doesn't even understand what the process is trying to do. It doesn't have the notion of the semantics of a process. It only executes operations. Yes, so what can the operating system do?
Use the previous data to estimate.
Yeah, it tries to estimate based on what?
The previous data, the accounting,
It tries to estimate based on history. So something that the operating system knows is the history. So I'm now trying to execute operation N. I'm trying to do operation N, but as an operating system, I have helped this process execute operations 1, 2, and 3 through N-1, and I can track the history. So the system can track the history of that process, so it can track the lengths of the previous CPU bursts, and based on the lengths of the previous CPU bursts, the system may try to predict the length of the next CPU burst. So the system doesn't know the future, but it can predict the future using the past. So this is what operating systems do. In fact, we will see this not only in CPU scheduling, we will see it in other operating system algorithms like memory management and disk management. So it's common for an operating system to try to predict the behavior of a process based on the future behavior of a process based on its past. And this is exactly going to be the next topic, which is a way or a scheme for predicting the length of the next CPU burst based on the previous CPU bursts. Yes?
Can't the process have information that will help the OS indicate just how large the burst time might be?
the process itself.
Because in memory, processors are represented on PCBs, and PCBs contain information about the process. So
Yeah, and this is where the operating system keeps track of the length of the, say, the length of the last CPU burst. So the system can easily store the length of the last CPU burst in the PCB, in the process control block. And it can save the, the length of the last CPU burst, or even the last 2 or 3 or 4 or 10 CPU bursts. It can track that, it can store it, and predict the future behavior based on that. So in fact, shortest job first is an algorithm that operating systems actually use, but they don't just use it in this simple form. They use it in combination with other algorithms and other criteria.